So now we are going to talk about chemical equilibrium. So what is chemical reactions, right? And chemical reaction is a process that leads to the chemical transformation of one set of chemical substances to another, right? So there is a changes, right? Transformation from one to another. And what is equilibrium? I believe you already heard about this term, right, previously in your chemical classes, right? And so this equilibrium, right? And these are the common term used when we are going to describe a chemical reactions, right? So whether the reaction is in equilibrium or not. So when the rate of forward reactions equals the rate of backward reaction, this is known as equilibrium, right? So the reaction is in an equilibrium state. And then what is stability and metastability, right? So this is another term used to describe the phases, right? The substance, the stability of substance, right? If we want to describe, for example, in a solid state, right? ACC, which is amorphous calcium carbonate, right? Or MHC, monohydrocalcite, or aragonite, or any others minerals, right? We want to describe it if it is stable or not under that particular condition, right? Calcite, quartz, right? So it depends on the temperature and the pressure, and also the types of what do you call contaminants, right? Or inhibitors is in the crystal structure of these minerals, right? So it may affect the stability of the minerals. So so what makes a system stable or a system which is unstable, right? We are going to look into this. So there are three requirements for mineral stability, right? And first one is the constituents, right? For example, the available reactants or the elements, right? How what's the composition of it, right? And what do you have, the reactant, right? And also the correct environmental conditions. This will involve energy, right? And one of the condition we often that greatly influence the mineral stability is always temperature, right? And also pressure. So I believe you heard about these, the Bowen's reactions, right? And you know which minerals is stable at which temperature. Like for example, these olivine is stable at a very high temperature, right? Approximately 1000 Celsius, right? Whereas olivine will not be stable, right, at a lower temperature. So for olivine to form, you need an environment with high temperature, right? Similarly, you have a pyroxene, right, which is stable at this temperature domain, right, somewhere in between the stability of the temperature that favors the olivine, and also the temperature that favors, for example, amphibole or biotite. And quartz will only start to crystallize, right, at a slightly lower temperature, right, which is around 750 degrees Celsius. So stability of these minerals can be clearly manifested in this boron reaction series, right? So this, in this diagram, right, you can find these percent of minerals by volume, and then at a different temperature. So here you have, it starts with 700 and until 1200, and you form different, because of the different composition of these minerals in these which is stable in this particular temperature regime. Then you have different types of minerals form, and therefore the different types of rocks. Okay, so you have different names for it. Peridotite, which is olivine rich. You have at least almost more than 60% olivine, and a little bit of pyroxene perhaps, right? And also you will have some calcium rich plagioclase, right, which is a much stable form of plagioclase, right, compared to at high temperature, right, compared to sodium plagioclase, which is much stable at the lower temperature domain, right? So whereas if for granite, right, to form, right, and you need quite a huge or large composition of potassium feldspar, right, and also a quartz and a little bit of biotite, and also a sodium rich plagioclase. So these will form this mixture when it all crystallize, right, with all these different mixtures together. Then you get granite when the crystallization process is slow, right? So the cooling process is slightly slower, so you get a coarse grain granite. If it is a rapid cooling, then you form fine grain rocks, right, which is rhyolite. They have the same composition, it's just that different grain size, right? One is coarse and another is fine. So from this end, right, you have a higher increasing silica content, and whereas at the other end, which is the ultramafic end, you have less silica, right? So you have less silica content. So more stable position is one of lower energy, right? Minerals may not be stable, for example metastable minerals, so minerals which is less or not very stable, we call it like as metastable, right? Or you may term or call it unstable. So minerals contain more energy than expected from their environment, because stability, you involve the energy in it, right? So less stable minerals will have a greater energy in it, right? So therefore it is much energetic, right? And is prone to disrupted, right? And then form a more stable lattice, for example, or minerals, right? So for example, you in this case, aragonite is relatively less stable compared to calcite, and over time, right, if you given a right condition, and over time, when diagenesis takes place, then aragonite will transform to calcite, which is a much stable and less or less reactive minerals, right? So when you have a calcite or aragonite together in one place, and if there is any changes in the environment, right? For example, maybe some temperature, right? Then or any pressure, then you the less stable metastable minerals will be prone to will susceptible to changes, right? It will transform to a more stable minerals. But this one, of course, we need to know if the process is endothermic or exothermic, right? So we need to see the also you need to consider the energy of it during the changes. So temperature is one thing, right? Is one thing to change the directions of these the reactions, right? So if it is a forward or it's a backward, so you need to know if the reaction is exothermic or endothermic reaction. So energy required to overcome metastability is the activation energy. So what is activation energy? Let's see the next slide. So it's the energy that required to change mineral phase, right? For example, if this is here you have energy, right? Energy increase in energy, right? If this is aragonite, so aragonite, as we know, is a metastable type of calcium carbonate, right? And then if you want to change aragonite some extra activation energy, so this additional energy need to apply on aragonite, so that these minerals will transform, right? You need to overcome the energy barrier, right? This is the energy barrier. So the activation energy need to overcome the barrier. So when activation energy is larger than the barrier, of the energy required for the barrier, right? So it will transform, right, to a more stable product, which is at a lower energy product, calcite. So therefore this is less this is more stable. So you can read this paper, interesting paper on about the transformation and crystallization energetics of the synthetic and biogenic amorphous calcium carbonate, and it's about the transformations of calcium carbonate, right? Biologically, it favors this rapid formation of amorphous calcium carbonate because it's easier to form, right? It is less crystallized, right, compared to a more solid or anhydrous phase, right, such as aragonite or calcite. So over time, when these bio induced calcium carbonate precipitations happen, right, it will start with the precipitation of or the formation of amorphous calcium carbonate, and then slowly it will slowly transform the calcium amorphous phase amorphous calcium carbonate will rearrange itself into a more ordered crystal lattice, right, which is also a calcium carbonate structure, but more solid and which is aragonite, right? And then after that aragonite, there is also, if there is further transformation, then you will turn to calcite, which is the ultimate or the most stable phase for the among these different calcium carbonate polymorphs. Okay. So for method stability, when method stability transfer or transform to a stable phase minerals, it often involve this process, the Ostwald ripening process. This is a process where the less stable minerals will rearrange or will undergo some dissolution and reprecipitated, right, or rearrange, right, or recrystallize as a more stable minerals, and usually is a much larger one, right? So Ostwald ripening refers to the growth of larger crystals from those of smaller size, and then which have a higher solidity than the larger one. So, for example, an everyday example of Ostwald ripening is the recrystallization of water within ice cream, which give all ice cream a gritty or crunchy texture. Right, so as I said just now, this ACC, amorphous calcium carbonate, which is the least stable phase calcium carbonate phase, right, compared to other polymorph. So especially ACC, this ACC, often you start with a nucleation of this ACC, right, amorphous calcium carbonate, which is in a very, very tiny in diameter, right? It's almost in a nanometer size or sub-nanometer size, right? So as ACC slowly transform to aragonite, for example, right, this ACC crystal will start to grow, right? And this growing process is actually one of process or the transformation process that involve these Ostwald ripening process. So in the aragonite minerals, we have a crystal that is which has this calcium and carbonate being crystals being rearranged and organized, right? And therefore this aragonite grows into often you have a larger crystal size. So this is probably in the micrometer micrometer in diameter for the aragonite minerals. Right, when you look in the SEM, you can clearly see the morphology of it, and you can see the size. You can easily measure the size of these minerals. So as I said just now, we have calcium, these transformations of calcium carbonate, ACC, amorphous calcium carbonate, then it changed to veterite. Veterite is a very transient phase of calcium carbonate as well. So all these are calcium carbonates, right? So it's just a different structure. So you have this term polymorph, right? And they are chemically identical, but the crystal structure is just slightly different. So you have the veterite and then aragonite, right? And then further transformation will eventually form a calcite, right? So in this y-axis you have free agent energy, and then on this x-axis you have the reaction coordinates. So as reactions goes on, right, and you have this transformation of this reactant to different product. So you have a much from a higher energy reactant eventually will transform to a much lower energy minerals. So besides in low temperature geochemistry, right, besides the impact or the influence of temperature and pressure, right, and on the stability of the minerals, right, we also have this biological influence, right, may also help in the in governing the stability of those minerals. For example, on this paper, right, there is this microbial sulfate reduction, right? These microbes actually creates an environment and also a condition where it helps with the precipitations of calcium carbonates, right, by using the cell, the bacterial cell itself, right, as a template, right, for minerals to precipitate on it, right, and then starts as a nucleation point for further growth of these calcium carbonate minerals, right? So bacteria also may help as a catalyst, right, that lower the activation energy required to require for transformations to happen, right? So it will help lower this activation energy. So bacteria may also plays a role in low temperature environments, right? So how stability be estimated, right? So it can be estimated by via algebraically, right? Which is the more on the physical chemistry of it, using these thermodynamics to explain, right, and to calculate the stability, which we are going to learn in the next few lectures. And then this involves the estimates of this free energy, the Gibbs free energy, right, the delta G. So another one, we can actually estimate stability by using this phase diagram, right? These phase diagrams are the diagrams that has been created, like, or has been experimentally validated, right? So you have these different phase diagram that people use, do different experiments of different temperature and pressure, right? And then they try in the lab, and also maybe some models, and then you may have maybe some different minerals at the stability of different minerals at different temperature and pressure. So it involves a lot of these experimental data, right, to make the phase diagram. So when we know what for example, the temperature or the pressure of these environment, right, and then we may know what kind of minerals are stable, right, and in that condition. So essentially figures of solutions to these delta G problems. So it may be many types. Common ones, you have one component, for example, the temperature and pressure variables, and then you have this X, right, being fixed, or two or more components. So for example, the temperature, right, and the X varies, but pressure being fixed. So next, when we talk about chemical reactions, right, and stability, we also have to introduce a little bit of acids and bases, right? So what's the use of acids? So the common usage of acids is the one of the character is it tastes sour, right? And then it's often being used to dissolve metals, right? If you still remember when you have acid, right, say acid reacts with metal, right, you will if you still remember, this one produce a salt and also hydrogen gas, right? So this is the general reactions of acids. You may form salt and the liberations of hydrogen gas, and it reacts with bases to form salt, right? So in geological use, right, igneous rock containing much SiO2, right, and then acid oxides, right, react with water to form acids, right, or base to form a salt. So usually non-metals, metals in high oxidation states, for example, sulfurous acid and sulfuric acids, SO3, and also carbonic acids. Okay, so these are some examples of the acids. And then current usage in chemistry, containing hydrogen that release these hydrogen ions into a solution when dissolved in water. So it's any chemical that be able to release hydrogen, right? Hydrogen ions into solution when dissolved in water. So for example, acid oxides, right? The oxides of period 3 elements demonstrates a periodicity with respect to acidity. Okay, and as you can see over the periodic table of element, if you move across the table from left to right, then you have this increasing in the acidic character of for the elements, right? So acidic oxides can also react with basic oxides to produce salt and oxyanions. For example, magnesium oxides, right? Magnesium oxide here, which is basic in nature. When you have these reacts with silica, right, and you form a magnesium silicates, right, and this is the salt, right? And then when you have these acidic minerals reacts with NaOH, which is basic or the base, right? You produce salt plus water. For base, right, is the opposite of acid, right? So current usage in chemistry, substance containing the OH group that release hydroxide into solution when dissolved in water. And for geological usage, basic oxides are oxides that shows basic properties in opposition to acidic oxides, and then react with water to form base, reacts with an acid to form salt and water, and you have often you have high pH water where water interacts with ultramafic rocks or serpentinite under a closed system, right? Because serpentinite, you have a large magnesium in these minerals, this type of ultramafic rock. You have abundance of magnesium dissolved in these in the minerals of these rocks, these pyroxene or olivine, right? So when it dissolves in water, then it reacts with water, and then you may produce water with high pH. Okay, because what you may form is this magnesium, for example, this silicate plus H2O, then may give you, right, magnesium hydroxide, magnesium hydroxide plus what do you call HSiO4. Okay, so these will promote the formation of these hydroxides, right, in the water, which is a basic in nature that will produce a higher or gives a higher pH. So here you have these examples of oxides reactions with water. So an example of sodium oxide reacts with water, what you get is sodium hydroxide and plus this hydrogen, right? And because of these hydroxides in the water, and it will create, or it will increase the pH of the solutions. Whereas for acidic oxide, for example, these sulfur dioxide and this sulfate, right, it will gives H2SO3, which is acidic, and H2SO4, which is also acidic, right? So you have more elements, these hydrogens, right? So hydrogen ions may dissociate and gives off this acidity to the water. So pH, right? So pH is defined as negative log of the hydrogen ion activity, right? Which is the concentration of hydrogen ion in a solution. So have you ever wondered why, right? Why we need a negative log for the concentration, right, to express the concentration of hydrogen ions in aqueous solutions, right? So it is because, right, the concentration for hydrogen ions in any solutions, right, is always very small, right? And bear in mind the unit for the concentration here is in molar, right? So when it is in molar form, right, so the concentration is often very small, about 10 to the power of -7, right? It means in normal water, you have the concentration for these hydrogen ions is 0.0000. It will be 7, 1, 2, 3, 4, 5, 6. What do you call? 1, 2, 3, 4, 5, 6. So 7, right? This is molar, right? 7 molar, -7, right? So this is a very low concentration, right, for hydrogen ions. So if you want to compare to, say, in seawater, right? Seawater has a, say, let's say this is hydrogen atom, right? If seawater, we have calcium, right, in seawater. So the calcium concentration in seawater is often is almost 10.4 millimolar. So if I make it to molar, it will be this one, right, divided by 1,000 to get a molar, right? So it will be 0 0.0104 molar, right? So whereas if it is hydrogen ions, the concentration in the seawater, right, seawater sample, we know that the pH for seawater is approximately 8, right? So it will be 0.00000 0.01 molar. So you can see how many times or how many fold difference in the concentrations, right? So the hydrogen concentrations in seawater, right, it's so low, right, compared to calcium. So it will be will have difficulty, right, to report these concentration, as there are so many zeros behind, right? And therefore for to measure solution in a more convenient way, right, we lock it, right? We lock it, and therefore when we lock it, we will have what do you call we only report the number of the zero behind. For example, this is when you log 1 times -8, right, what you will get will be 8 and negative, right? But if we to get rid of these negative in front, then we negative it, so therefore you get a negative log here, so it will become a pH of 8, right? This is for convenience purpose, right, for convenience sake. So this is why we use the term this negative log, or which is known as P, right? P equals is a short form for negative log. You could have any like P calcium, right? P calcium, it means a negative log of these calcium ions. You can have P of whatever thing, right? Whatever subs POH, for example, POH hydroxy, whereas this is for the hydroxides concentration. So for these concentrations of hydrogen, right, to be more accurate is actually not measuring the just the hydrogen ions. We are actually measuring the activity of these hydrogen ions. I'll talk about activity in the next slides, I think, or the next few slides, right? What is activity about? So here I already explained why we use negative log. All right, so at 25 degrees Celsius, so water dissociates. So you have this water dissociation constant. All right, first water, it dissociates into hydrogen and hydroxide ions, right? And has a dissociation constant of 10 to the power of negative 14, right? So how this is calculated, right, or how this is derived, is actually the Kw, the constants for water here, dissociations of water, constant, right? You report the product over the reactant, right? So you can rewrite it as HOH here and divided by H2O, because this is a liquid, right? Liquids, there is no it will not involve in any reactions, right? So it is just liquid water, whereas here you have these hydrogen ions and hydroxide ions constantly dissociate and also bind together. So there is an activity, and there is always constant reactions. Therefore, we take these into account, right? The concentration for this one, the hydrogen of concentration for it, which is 1, right, to the power 10 to the power of negative 7 molar, right, times this one is for the hydrogen ions, right? The same one also for hydroxide ions, right? And what you get will be the constant for the water dissociation, right? So in neutral solution, H equal OH, right? The concentration, right? You have 10 to the power of 7, right? Which is also pH 7, right? So you negative log, right? You get 7. Okay, so calculate the pH when Kw equals 6.5, right, times 10 to the power of 14 mole, right? So you get how do you calculate this, right? What's the pH? To calculate the pH, this is given, right? So this is given. Then if you back calculate, right? So the first thing, because you have both here, you have both H and OH, right? The concentration for hydrogen and the concentration for hydroxide, right? So here you have 2, okay, and they are here the relationship between two, the calculation is Kw. You have these 2, so there is x 2 here, right? Because you have x to the power of 2, then if we want to back calculate it, we square root it. So what we do is we take the square root of this Kw, right? And then negative log to find the pH, right? You negative log when you get x, right, and this one will give you when you square root it, you'll get x, right, and then x is the concentrations of either H or OH in this case. Okay, so when you have the concentrations of X, then you want to find the pH, right? So you negative, if you still remember, we negative log the concentration of the X here, or the hydrogen ion. So therefore it will give you a pH of 6.59. Right, when you do the calculation, you square root these and then negative log the answer of this square root, you get 6.59. So this is how pH is can be calculated based on the concentrations of the hydrogen, right, in a chemical reactions. So as I mentioned in the previous slide, there is this A over here, this term, which is the activity, right? This is the activity of hydrogen ions, right? So what is activity? Right, so before I talk about activity, right, I would like to talk about the different types of species, right, that will that is in for example, seawater. Okay, so let's say I sample 1 beaker of seawater, right? So this is a beaker, and then this is the seawater sample that I collected from Port Dickson. Okay, so you have seawater sample here. Okay, so what's in the seawater? Say if I filtered everything, right, there is no biological component there. There is everything is already being filtered out, right? And what's inside is just the dissolved chemical components, right? So now we are talking about chemical species in this beaker. So what do you find in this seawater, right? So seawater, as you know, is a water, right? So you have H2O, all right, and then you have also calcium, right, dissolved in seawater, and then you have a lot of sodium, right, because seawater is saline, right? So sodium, and then also you have magnesium, and then you have also potassium, right, in seawater. Okay, these are cations. So these are the cation species, right? For anion species, what do we have? We have sulfate, right? We have plenty of chloride, right? That's what gives this salinity, right? You have sulfate, you have chloride, you have sodium, right? All these ions, dissolved ions, actually gives the or contributes to the salinity of the seawater, right? You have plenty of this, right? And then also you have plenty of chlorides, then you have sulfate, and then also you have a little bit of fluoride, right? And you may have some bicarbonates as well, right? And then you may have some bromide, right, and maybe a little bit of iodide. So these are the components, right, that you may the species that you may found in dissolved form in seawater. And also H2O, because of water here, right, as you know, H2O, water molecule, will always dissociate, right? It will dissociate into H and OH, right? And then later on it will bind together to form hydrogen ion. These reactions is always happening, right? It is reversible reactions, right? It keeps dissociate and then binds with opposite species of opposite charge, and you get to H2O again, right? So what's inside here, you have also, right, so this should belongs here, right? So this will be H, the H species, and here the anions, you have OH, right? These are the anions. So this is what we got, right, here inside the seawater. And because of the high salinity of high concentrations of this seawater, salinity of these minerals or these elements, right, you have very high sodium and chloride, right, and it is so concentrated until a point where you have some of these ion pairing happening, right? Even imagine that you have all of these ions, a lot of these sodium, a lot of chloride ions, and it dissolves in the water, and it is so congested, right? So when these free ions are so congested, they congest together, what will form? You form, and you tend to form some ion pairing, right? So maybe some say some sodium, right, may temporarily bind with bicarbonate, right? This 0 is the charge, so there is no charge over here. So it will again dissociate. This is just this is very unstable, so it may dissociate quickly. It forms and dissociate quickly into sodium again and bicarbonates ions, right? These positive and negative charge ions may constantly bind and then dissociate again, right? So if you get all these more and more concentrated and more congested, then you get this more affinity or more possibility of this pairing to form, right? So this is seawater compared to if this is rainwater instead of seawater, right? You have a very less amount of these cations and anion dissolved in it, so you have plenty of space, and these free ion actually didn't interact, don't have the chance to actually interact together, right? So in rainwater, which is a very dilute water, right, the chance of this sodium bicarbonate formation of this sodium bicarbonate ion pairing will drop, right? It will be very less chance of this forming, right? So this comes the reason why we need to consider activity. So activity is the chemical species, for example A denoted by this, right? This is the concentration or the activity, not concentration. So this, if we use bracket, right, of A, this is the we are talking about the concentration. If we use these semicolon, it will be known as activity. So meaning that if I draw H like this, right, with the bracket here, then it means that this is I'm talking about the concentration of the H. If I draw this one, it means with the these brackets, small brackets, then I'm talking about the activity, right? So this denoted by this one, right, is related to the concentration of this species A by the activity coefficient. This one, right? You have what you call gamma, right, of A. So the activity is denoted by the gamma, right? So this gamma is the activity coefficients, right? So ideally the activity coefficients is 1, right? In ideal solution, in ideal solutions means that solutions where you don't form any of this pair, right? It's a very dilute solution, right? You don't these the chances of forming this sodium bicarbonate or any ion pairing will be very low, right? So it is these ions is always in its free what is is freely available. It is not bind to any other ions with opposite charge. So this is freely it always appears as a free cations, right? And then carbonates always appears as free anions. So when there is no ion pairing reactions happening, and these in very diluted solution, then this is what we call as known as, this solution is known as ideal solution, right? But in normal environment, ideal solution is almost impossible, right? You will always have for example, in river water, right? Although river water or rainwater, they are quite dilute, but still you might have some chance of these ion pairing to happen, right? So it is some sort of a little bit of deviate from ideal solution. So these deviations lead to the non-ideality of the solution. And for ideal solutions, the activity coefficient is always 1, right? So this is always 1, right? The activity will always be 1. So 1 will referring to the infinite solution activity. So we are talking about the activity, right? Is 1 for which the concentration of all solutes approach 0. Right, so which is very dilute, right? So in dilute solution of simple electrolytes, deviation from ideal behavior are caused by long-range electrostatic interactions. Okay, so this is because when ion pairings happen, right, it's because of these electrostatic interactions, right? Why the bonding, the transient bonding between the sodium, for example, this ion pair, the sodium bicarbonate, is actually this electrostatic bond, which is a very weak bonding, right? So very weak types of bonding. So in seawater, the measurements of activity is more complicated. So because of the high ionic strength of seawater, right, you have high concentration of these cations and anions that dissolve in this seawater, right? And therefore leads to the ionic strength, and various or different ions with different charges inside. So you have ions with two negative charge and two positive charge, right, for magnesium, right? So or sodium. So they have different charges, right? And these different charges may attract different anions to it, right? For example, calcium attracts sodium with two negative charge, so they will be favored to bind together and then dissociates again. So these sort of interactions always happening in these any solutions, right, that we prepare in seawater, especially. These will be more apparent because of the high concentrations of these dissolved ion in it. So ion pairing and complex formation in electrolyte mixture and can be calculated theoretically using the Debye-Huckel equation, the Davis equation, or the Pfizer, or this specific ion interaction theory, which is the SIT. Right. So these are some of these what do you call the algorithm that we use to calculate, right, or define the activity of for these ions, cations and anions under different types of solutions, right? So this is sort of when we use this algorithm, we may use it in to model what's condition or what's the species it will form, right? For example, in this table 5.3, so you have these dissolved species, and then you have the activity coefficients, right? So these dissolved species, you have magnesium carbonate, calcium carbonates, right? And these are very transient species, right? But if you have a very high concentration of water with these cations and anions, then you have more of these being formed, right, in the solution. So the activity coefficient will get higher, right? So so these are some example of the ionic activity coefficients for the ion pairs at 25 degree and 1 atm. So bear in mind that it will change as if we change the activity of a coefficient would change if we change the salinity, right, or the temperature and the pressure of it. So activity means just now, just to recap, right? Activity means the free ion, the activity of this free ion, right? If it binds, right, with what do you call some other anions, right? The activity will decrease, right? The activity for this, for example, sodium, right? If you bind with HCO3, then if there is a lot of this in the solution, then the activity will decrease. So the free, it means that the free we have less free sodium in the seawater, right? Because some of the sodium may have formed this transient species here, right? So therefore you may have an activity of sodium which is less than 1.0, maybe around 0. Here say 7.6, right? So this is why in non-ideal solution you always have an activity of any ions, right, which is lesser than 1.0. If you have a very dilute solution, right, then the activity will always approach, right, or near close to 1. So this is ideal about the activity coefficients, and also the ideal of these dissolved species in any aqueous solution. Okay, so I won't go in detail into the activity coefficient, actually how to calculate it and how it was derived and calculate the species, right? I won't go into that. It's a large chapter to talk about these, and I just want what I want here you guys to understand is just an idea what activity coefficients, right? We don't actually to accurately measure concentration, right? We don't measure just the concentration, but we measure the exact ions, right? The freely available ion, for example the sodium, right? We don't measure in instruments, we don't measure sodium bicarbonates, right? And all these will be nebulized, and you form this freely available sodium, right? And the actually this is what the instruments reports the concentrations, right? So this we should be clear, right, about the usefulness of this activity, right? It is useful, especially when we model. We want to model what sort of species and the concentrations that we will get, right? We are supposed to get, right? So this is the idea of the activity coefficient. So what about, so when we talk about pH, right, just now, then what about pH at 200 degrees Celsius? Will it be the same, right? And why it will be different, right? So if you still remember just now, if the pH of a pure water at 25 degrees Celsius, the Kd or the Kw is 10 to the power of negative 14, right? But now when the temperature increase, the Kd for the same pure water increases, right? So now it becomes 10 to the power of negative 11, right? So why there is different, the Kd is different when you have a different temperature, right? Think about it. Why? So actually these will involve the chemical reactions, right? The types of chemical reactions for the dissociations of this pure water, right? Because these formations of these hydrogen ions, right, and hydroxide ions from water is an endothermic process. Endothermic process. I am not sure if you still remember what is endothermic, right? So endothermic process is a process where you actually if we are talking about forward reaction, right? Okay, the dissociation. So this, you may absorb heat. Actually, to break the bond of H2O, you need to absorb heat to break the bond in order to dissociate, right? This to break the bond between H2O to form a freely available H and OH here, right? So this process is endothermic. And if the process exothermic is the process where you release, right, energy, right, and when energy or heat is released, the reaction is exothermic. So exothermic can be manifested as in this backward reaction, right? So you need to release the energy for these two to form, right, to form a bond, to form a H2O molecule. Okay, so here you have this because this forward reaction is endothermic, right, and because of Le Chatelier's principles, and I think we are going to talk about this Le Chatelier's principle, right? So it's about the equilibrium, right? The reaction dynamic equilibrium. So it talks about something when the position of equilibrium will moves to counter the change that we made, right? So if we say if this is an endothermic reaction, for example, and if we increase the heat of this solution, right, this reaction, and the equilibrium actually tends to favors the reaction that to counters the increase in temperature. So what will it do? It will tends to so in this case, actually it will tends the equilibrium will tends to lower the temperature, right, the system, right, because the system has a high temperature. So these reactions actually will favors the reactions that can reduce the temperature, right? So to lower the temperature for these reactions, you need you will favors the forward reaction, right? It means that it will go to the right, the reaction will go to the right, and you have more energy being absorbed actually to break the bond and form more of these free ions, right, the hydrogen and hydroxide ions, right? So therefore when you have more of this, it means that the concentration of these increase, right, of hydrogen will increase. So do the same, right, for hydroxide ions, right? So as when both of these concentration of these ions increase, right? If you still remember, how do we write out the equation for the Kd, right, or the Kw is the product over the reactant, right? So this is the product, right? And then over the reactant H2O here, which is liquid. So when you have the concentration of both of these increase, right, it means that the product will increase, and you have this reactant, right? This reactant will decrease, right? If this, so when you calculate the concentration for this one, right, the hydrogen and the hydroxide ions, then when these value increase, then it means you increase the KD, right, or the KW, right? So KW will increase because you increase the both of these reactants, these products. Okay, so therefore when it is at the solution is at a different temperature, right? So we have to take note about the types of reaction, whether if the forward reaction is endothermic or exothermic, right? So we have to take note about that. So in neutral solution, the H and OH equals pH of 5.5, right? It doesn't mean that at 200 degrees Celsius, when you measure the water, right, of pH 5.5, it doesn't mean that the water is actually acidic. It's not. It's because of you have a greater, because pH you measure the hydrogen ions, right, in it. So you have greater concentration of H, of course, at the same time, because it dissociate the water, more water, liquid water is being dissociated. Then you also have the same amount of OH as well. So when water dissociates, you produce these two. So when this increase, right, you produce more of these. These also you get the same time also increase, right, in the solution, right? So actually, it doesn't mean that when at a higher temperature, when we measure the solution at higher temperature and get a pH of 5.5 or lower than 7, it means that it is acidic. It is actually neutral state, right, at this point, because of the higher concentration of hydrogen in it. Okay, so pH can be negative if the acids use a concentration of hydrogen ions with a molarity greater than 1. For example, 12 mole of hydrogen chloride can give a pH of negative 1.08. So in theory, negative pH only exists in calculation, right, and acid error or incompatibility situations of acids. So here you see the chart, right, plotting the solution with increased acidity, right, and the types of solutions that increase the basicity of it, right? Pure water at 7, right, and then seawater 8, 8.2, right, 8 to 8.2, and then baking soda you have some pH of 9, right, until you have NaOH, right, which is you have a pH of 14. Okay, and in the other spectrum of these pH, you have saliva, right, our human saliva, which is slightly acidic, which is a pH of 6, and then orange juice, right, because of the citric acid, right, and therefore you have this a pH of 3, and then at last you have this HCl or this battery acid, which is very acidic, which you get a pH of 0 or close to 1. Okay. So this, bear in mind, this one, the value of this pH reported in 25 degrees Celsius and 1 atmosphere. Okay, so it may change as we increase the temperature or decrease the temperature, as I show you just now in these calculations. So you can look through this, right? The pH and the at 25 degrees centigrade, and how this equation is being derived, right? So how do we measure pH? Actually we use a pH meter, right, or litmus paper, right? If you still remember in your secondary class, right? So these are some of the methods. So I think I'll talk more on these, right? How we measure pH in the next lecture, right? So I'll stop here and continue in the next lecture. Thank you very much.